Hello everybody and welcome to our presentation for Middleware Conference 2021 titled Let's Wait a While, How Temporal Workload Shifting Can Reduce Carbon Emissions in the Cloud. This was a joint work from researchers from the Technical University Berlin and Hasso-Plattner Institute at the University of Potsdam. Our talk follows the general format of presentations at Middleware Conference this year, meaning that the first 10 minutes cover a full overview on our paper. I'll start with some motivation and background on carbon-aware computing, describe some characteristics of shiftable workloads that are relevant for our research. I will quickly summarize our analysis and evaluation sections and then get to the most important part, the consequences for cloud and service providers that follow from our findings. Then I'll conclude the first half. And in the second half, we will go a little more in depth on some topics. We'll discuss whether the average carbon intensity, which is the metric our work is based on, is actually the best grid level signal to motivate carbon-aware load shaping. And next, I will present some more findings from our analysis and evaluation. And lastly, I'll point out some possible future directions of research. So let's get started. Data centers currently consume well over 200 terawatt hours of energy per year, which is roughly 1% of the global energy consumption. This fraction was fairly stable during recent years due to the continuous shift towards efficient hyperscale data centers. However, the consumption is expected to again rise further in the future. So there are different forecasts on this, but even when looking at best case scenarios, we're talking about 3% by 2030. And this brings us to the idea of so-called carbon-aware computing. There are also the terms renewable-aware computing, carbon flexing, 24/7 carbon-free, etc. And they all describe similar or sometimes even the exact same idea. And this idea is based on the fact that in electric grids around the world, the fraction of renewable energy sources like solar and wind is rising, which is resulting in a growing variability of energy production. So depending on the installed energy sources, weather, demand, energy imports, etc., a kilowatt hour of consumed energy is not always associated with the same amount of CO2 equivalent greenhouse gases. This metric is also called carbon intensity, so the amount of emissions per kilowatt hour of energy. You can also see this in the plot on the bottom right. So in other words, to reduce your carbon footprint, it does matter when and where you're consuming energy. Other than energy efficiency, which aims at reducing the amount of energy we need, carbon-aware computing aims at consuming energy at the right time and at the right location, namely where and when low-carbon energy is available. Now, in this paper, we focus purely on the timing aspect and do not consider geo-distributed scheduling. For this, we analyzed the average carbon intensity of 4 regions, Germany, France, Great Britain, and California over the year 2020, as the question of when to schedule workloads is not trivial and depends, as I just said, on different regional characteristics. Our research question, therefore, was what is the carbon saving potential when performing temporal workload shifting in data centers with the goal to reduce their carbon footprint? What is the impact of certain workload characteristics on this potential at different times in different regions? And also we wanted to generate insights on the theoretical limitations of this approach. To better understand what a shiftable workload is and what properties are important, we first define some characteristics of these jobs. The most important characteristic are the temporal constraints of a workload. You could also call this deadline, but we'll see in a second that some workloads cannot only be postponed into the future, but can maybe even be computed earlier than originally planned. Second, the duration of jobs is of course very important, and even more whether we can predict this duration with somewhat high accuracy. Third, we differentiate between what we call ad hoc and scheduled workloads. This is shown in the figure on the top right. So what we mean by ad hoc and scheduled is ad hoc jobs are issued at the current point in time. For example, a continuous integration run that was triggered by a commit. We might be able to defer them a little, but for sure we cannot compute these jobs any earlier than now. With scheduled jobs, we describe jobs that are scheduled in the future. For example, nightly integration tests. These kind of jobs might also be computed earlier than originally planned. Lastly, the interruptibility of workloads can play an important role. You can see this in the figure on the bottom right. Some workloads like long-running stress tests cannot be interrupted. Other workloads can be interrupted, but stopping and resuming them is very expensive or time-consuming, so it's not really meaningful in practice. Other workloads, however, like machine learning training jobs, usually already have checkpoint mechanisms built in for fault tolerance, etc., And we can exploit this property by computing such jobs during different local minima in the predicted future, so in the predicted future carbon intensity, to reduce the associated emissions even further. Next, I want to provide you a quick overview on the analysis section of our paper. We analyzed the average carbon intensity of Germany, Great Britain, France, and California over the year 2020. You can see the average daily carbon intensity by month in the figure on the slide. Daily patterns vary highly from region to region. So, for example, the carbon intensity in France is very low and very stable throughout the entire day, as France produces most of its energy through nuclear power. On the other hand, in regions like Germany and California that have a lot of solar power, we notice significant drops in carbon intensity during noon, when a lot of sun is available. On some days, the difference between 12 o'clock and 6 p.m. can be up to factor 4, meaning energy in the evening is responsible for more than 4 times the CO2 emissions than during noon. Another common pattern is reduced carbon intensity at night, where electricity demand is generally lower. Weekly patterns are more uniform across all regions, with the general rule that energy is cleaner on weekends, which again has to do with lower general demand in electricity. More details on this analysis and the carbon metric we used are provided in the second half of the presentation. Building on the analysis, we evaluated the theoretical potential of carbon over workload shifting in 2 different scenarios via simulation. The first scenario covers scheduled jobs like nightly builds, and the second scenario is looking at ad hoc jobs, namely we are simulating a big machine learning project. Again, details are discussed in the second half of the presentation, but you can already see that, for example, in the second scenario, which is depicted in the figure on the slide, we were able to reduce the overall carbon emissions by around 10% in many experiments. Before we conclude, we will now talk about the most important part that follows from our findings: possible measures for cloud and service providers to make use of temporal workload shifting. The first measure is to directly incentivize customers to use compute infrastructure when the carbon intensity is low. A mechanism for this is already in place for all big cloud providers. Amazon calls them spot instances, Google and Microsoft spot VMs or preemptive VMs. And what they do is already load shaping. They offer compute power at a lower price to incentivize customers to use it at certain times. Now, carbon awareness can simply be integrated into these mechanisms by incorporating some grid-level signal into their pricing. However, there are several problems with this approach. First, it's less profitable for providers since they have to reduce their price to become carbon aware. Second, they move all the hard work and all the responsibility to design interruptible or preemptive workloads to the customers. And third, they only incentivize usage. There is no guarantee that workloads will actually be scheduled at the preferred times. So what is a lot more sensible for providers in many cases is to do the scheduling themselves. For this, they need, of course, flexibility. And one way to achieve this is by adopting service level agreements. For example, by promising users to schedule a periodic task during a certain time window, such as nightly, instead of a fixed point in time. The main issues with SLAs, however, is that they cannot be adopted frequently. Carbon intensity patterns, on the other hand, change over time and differ per region, so it might be difficult to define optimal SLAs that remain useful over long periods of time. The way more dynamic approach is to encourage users to design and declare flexible workloads. Now, for performing optimal scheduling, providers want to gather as much information as possible on the workloads. And this can be achieved in 2 ways. On the one hand, providers can offer APIs that incentivize flexibility. For example, I recently stumbled over the idea of integrating a hook in continuous integration services that executes a certain task, like a daily integration test, when the carbon intensity is expected to be the lowest, contrary to specifying an exact point in time. On the other hand, not all properties of jobs need to be declared by the users. Many can automatically derived by smart services and smart middleware. Estimating the runtime of workloads is already a common problem in scheduling. Services can profile the stop and resume times of workloads to determine their interruptibility. And if, for example, dependencies between different workloads are known to the service, it may even be able to derive deadlines. And with this, I want to conclude the first half of my talk. I presented an analysis of the theoretical potential of carbon-aware workload shifting with the goal to reduce the carbon footprint of cloud computing. Our findings suggest that shifting workloads towards times with low average carbon intensity can reduce emissions by around 5 to 15%, in extreme cases even by a third. Cloud and service providers can make best use of this approach by incentivizing their users to design and declare flexible workloads. In the second half of the presentation, we will go a little more in depth on some topics. Then we will discuss whether the average carbon intensity, the metric we based this paper on, is actually the best grid level signal to motivate carbon shifting. We will discuss some more findings from our analysis and evaluation. And lastly, we will talk about possible future directions of research. All code and datasets used in this work are publicly available on GitHub, and please feel free to contact me for any questions, suggestions, or collaborations. Thanks a lot for listening. So, welcome to the second half of the presentation. The first topic I want to talk about is whether the average carbon intensity is actually a suitable metric for carbon-aware load shifting. This is a topic that we discussed heavily during the creation of our research and that also pops up in every discussion about it. So to recap, we computed the average carbon intensity by weighting all current energy production and energy imports by their associated carbon intensity. We used an IPCC special report on renewable energy sources and climate change mitigation for this that considers the full life cycle emissions of energy production, so also renewable sources have some emissions associated to them. For example, according to the report, 1 kilowatt hour of energy production by wind energy is responsible for 12 grams of CO2 equivalent emissions, while 1 kilowatt hour produced by a coal power plant is responsible for 1,000 grams of CO2 equivalent emissions. Now, the nice properties about this metric is that it is very easy to compute if you have access to the electricity mix of a region. And it's also very easy to predict, which is of course very important in temporal scheduling. Additionally, it's a useful indicator to describe at what times most energy is stemming from low carbon sources. And these properties make it the most popular choice at the moment. For example, also the latest Google publication on their carbon intelligent computing system uses average carbon intensity as their main metric. However, there are obvious problems associated with this metric, as it does not properly reflect the complex cause-effect relationships of the electricity market. Because what you're actually interested in when shifting energy consumption is not what is the average emissions now and what's the average emissions in 5 hours. You want to know which power generator is throttled down if I consume less energy now, and which generator has to produce more energy when I use this energy in 5 hours. This generator is also called the marginal generator. In regions with lots of wind energy, for example, it can happen that providers have to reduce the amount of energy a wind park delivers because there's not enough demand. During these times, consuming additional energy is almost free, speaking from a carbon perspective. However, if the production of a coal power plant needs to be increased to address your usage, that is of course a lot worse. A metric that describes the carbon intensity of the marginal generator is the marginal carbon intensity. But while marginal carbon intensity is a great idea in theory, it is almost impossible to compute in practice due to the decentralized nature of the electricity market. So there are many different actors and their behavior depends on a lot of different factors like price, contracts, again, weather forecasts, energy surplus in neighboring regions, and so on. Some companies like Tomorrow, the company behind Electricity Map, try to predict this metric via machine learning, but this is a very hard problem and you end up with probabilities which might not be sufficient if you want to guarantee something like 24/7 carbon free. So we actually talked to Tomorrow, we talked to Google, we talked to other organizations that try to do carbon-aware load shaping in the building sector, for example. And it turns out that this topic is a topic for everybody and it's actually an open research question for all of them. For now, average carbon intensity seems to be a reasonable choice, but this may change in the future. So next I want to talk a little bit more on the analysis part of our paper. On this slide you can see the best times of day for shifting. So I'm not going to explain the plot in detail, but as an intuition, the darker and the higher this curve is, the more potential we have at a certain time of day of shifting workloads. And for now, I want to concentrate on this +8 hour window, which means what's the shifting potential of a workload that was originally supposed to be computed at a certain time if we had a chance to delay it by up to 8 hours. And we can see directly that this potential varies highly at different regions. In Germany, for example, we have the highest potential by postponing workloads that were issued in the early morning hours, because a few hours later we usually have more solar power available. And we have high potential in the evening hours, where energy is usually dirtier than at night. For reference, I'll now show you again the plot of the daily average carbon intensity that we have seen in the first half of the talk. In Great Britain, we have less solar installations, so here we only have the high potential in the evening hours. In France, carbon intensity is very low already, and also there is only very little variations, so there's almost no potential in this region. In California, we have huge potential during night and also during the early morning, as energy is a lot cleaner during daytime in this region. From this we can conclude that there's no general rule valid across all regions on when not to use energy, which always depends on the region and also season of the year. Now, before we conclude this talk, I also want to go a little more in depth on the experimental evaluation. We evaluated two scenarios. The first one was looking at periodic jobs, so for example, nightly builds, nightly integration tests, database backups, and so on. Our baseline experiment is scheduling such a workload every night at 1 a.m., so at a time where carbon intensity is usually already low. And then we computed the average emissions of this recurring workload over the year 2020. You can see the results on the very left in the upper plot. So for Germany, such a job emitted around 300 grams of CO2 per kilowatt hour, in France only 50. Now, we assumed that for many of these nightly jobs, customers are not interested in the exact timing. All they want is to have, for example, a nightly build of their app. As long as it's there in the morning when everyone's back at their desks, we can compute it at any time we want. So in our experiments, we continuously increase the time window we have available, starting at plus minus 1 hour, so from midnight to 3 a.m., up to plus minus 8 hours, meaning from 5 in the afternoon until 9 in the morning. The results can be seen in the plots. In California, the additional flexibility in the last experiment was reducing the emissions by up to 1/3. All experiments were applying some random noise on the forecasts to better resemble realistic and accurate forecasts. In the second experiment, we were looking at large ad hoc jobs. So we were trying to simulate a large machine learning project based on real energy consumption data reported by a recent NVIDIA publication on generative adversarial networks. So based on this paper, we assumed that around 3,400 jobs of variable length were issued during working hours of a year, and then investigated the impact of postponing such workloads either until the next morning when the data scientists are back at their desk, or even postponing them until 2 dedicated deadlines per week. Again, the assumption is that humans need these results, who do not care whether the job is finished at 2 in the morning or at 7 in the morning, as long as it's done until they're back to work. Scheduling until the next workday was reducing emissions by around 5%, scheduling in the semi-weekly scenario even by around 15%. Exploiting the interruptibility proved to be a useful strategy across all experiments. For more details, please refer to the paper directly. Regarding future work, we have two main directions we want to look at. First, as I stated before, our current work is purely based on data analysis and simulation, and therefore very theoretical. In our simulation, we also did not consider real-life constraints, such as limited availability of resources. Therefore, in the future, we want to move more parts of our evaluation environment to actual systems. For example, we are currently working on a carbon-aware Kubernetes scheduler. Using these tools, we want to develop and propose concrete carbon-aware scheduling approaches. So for example, there has been a very recent publication by Google on their carbon intelligent computing system that follows the same goals as the ones that we described in our talk. However, the combination of carbon-aware temporal and geo-distributed scheduling is barely researched at this point in time. The second direction is more targeted at future computing environments such as fog and edge computing, and in particular we want to investigate edge nodes with on-site power generation and storage, for example a roadside unit with a solar panel and a battery. This is a lot more challenging because most edge computing workloads are inherently time critical. So in other words, tasks have to be computed as fast as possible and as close as possible to their data source. However, there are also certain workloads that have a little more flexibility, that are not as time critical, and scheduling these at the right time can reduce the carbon footprint of edge infrastructure, but it can also increase resilience since we can avoid running out of battery in situations where there's no grid power available. Again, thanks a lot for listening to our talk, and please reach out to me in case you have any questions or ideas. Thank you.